In this video, I'm going to look at a second example on hypothesis testing. Let us suppose that in the year 2010, 25% of elephants in a wildlife park were male. 8 years later, in 2018, a game warden claimed that the proportion of male elephants had changed. That could be increased or decreased. In a survey in 2018, there were 10 male elephants in a sample of 50. Is there any evidence at the 5% level of significance to support the warden's claim? Well, let's start this off. We have to put down, first of all, the null hypothesis. Now that we have to write H0. And in this case, H0 is going to be the null hypothesis, no change. So that is your null hypothesis. Basically, both years, 2010, 2018, are the same. Now, H1 is what is called the alternative hypothesis. We are asking whether the proportion of male elephants has changed. So if we assume they haven't, the alternative hypothesis, what we will conclude if we reject H0 is that P has changed. In other words, that it's no longer equal to 0.25. We have a 5% level of significance. And we are going to reject H0 if the value of P is too great or too small. In other words, we have a two-tail test. As I've just said, the warden's claim will be rejected if the number of elephants in the survey is too large or too small. This gives us a two-tail test. This means we need two lines on our histogram, sharing the 5% at 2.5% either end. Now, we cannot do exactly 2.5% because of the discrete nature of the probability. And very often when we have 5% shared between 2.5%, we are asked to take the closest value to 2.5% at each end. So that the area up to the blue line is the one which is closest to 2.5% at this end, and the area beyond the blue line is the one which is the closest to 2.5% at that end. Let's show how we work that out. We have that X, the number of elephants, is binomial. Sample size was 50. And from the hypothesis, the probability was 0.25. That was my H0, P is 0.25. At the lower end, we can look in our tables and we see that probability that X is less than or equal to 7 is 0.0453. If I want to make that smaller at the lower end, I've got to make the number smaller. I've got to go below 7. X less than or equal to 6. If we look that up in our tables, it's 0.0194. Now, any other values, if the number gets bigger, then the percentage is going to get bigger. If I go down to 543, this will get smaller. 0.0194 is the closest to 2.5%. So my lower critical value is 6. That's right, x equals 6. Okay, let's go to the other end. At the upper end, we have, if we look in our tables, the probability that x is greater than or equal to 19 is equal to 1 minus probability x is less than or equal to 18, which is 1 minus 0.9713, which is 0.0287. Now that's bigger than 2.5%. So I need to move so that we have something which is smaller. I need to make the number larger. X greater than or equal to 20 is 1 minus the probability that x is less than or equal to 19 is 1 minus 0.9861, which is 0.0139. Doesn't take much to notice which of those two is closest to 2.5%. And so my upper critical value is x equals, it's the 19, x greater than or equal to 19. And so the critical region is x less than or equal to 6 or x greater than or equal to 19. If my test statistic lies in that region, then I reject H0. Otherwise, I accept H0. And we can see this on the graph there. That we have probability x is less than or equal to 6 is 0.0194. That's just gone over the top of the page, 0.0194. And the probability that x is greater than or equal to 19 is 2.87, 0.0287. We were told in the problem that there were 10 male elephants. So our test statistic is 10. Is x equals 10. If we look, the critical region is still just at the top of the page, which does not lie in the critical region. If the statistic does not lie in the critical region, it's in the middle here. It's in the bit where we're not surprised. We accept H0, and we conclude that there is evidence that the proportion of male elephants has not changed. We're not able to work exactly to 5%, and in this case, we are 1.94% down at the lower limit, an area of 2.87% at the higher limit, and therefore the actual level of significance is 1 plus the other, which is 4.81%. So if we're in that area, 4.81%, either this end or that end, we will reject the null hypothesis. We will reject H0. It is, of course, possible that it might be true. There is 4.81%, 0.0481 probability that the null hypothesis is true. And so the level of significance of 0.0481 is the probability that we reject H0 when it is in fact true. I've summarized that here, that the actual level of significance is the two areas added together, the left hand and the right hand, 0.0194 plus 0.0207, which gives us 4.81%. The significance level is the probability of rejecting H0 when it is in fact true. We now have a summary of the various things that you need to remember. The null hypothesis. This is what you assume to be correct unless you are shown otherwise. In other words, unless the test statistic gives you a significant answer. The alternative hypothesis. This is the conclusion that you should make if you reject H0. Hypothesis test. This is quite a mouthful. You do need to know it. A mathematical procedure to examine a value of the population parameter. In the case we've just dealt with, we were looking at the proportion or the probability P, proposed by the null hypothesis H0 compared to the alternative hypothesis H1. The test statistic is a little bit more straightforward. This is the statistic. Statistic has to be calculated only from the sample, which is tested. Usually tested in cumulative probability tables, or later we will meet testing with the normal distribution. And this is the last part of your test, apart from the conclusion. The critical region. The critical region is the range of values which would lead you to reject the null hypothesis. The actual level of significance is the probability of rejecting H0 when it is in fact true. These are more important than perhaps you might think. This is the sort of question that your examiner is sometimes keen on asking. What is meant by significance level? What is meant by null hypothesis, etc. The next little bit is basically how you should write out your solution. Both null and alternative hypotheses must be stated in symbols only. H0, P equals 0.3. Or if you're dealing with Poisson, H0, lambda equals 7. H1 is what you would do if you reject the null hypothesis, and it also determines whether you use a one or a two-tail test. So H1, P greater than 0.3, one-tail test. P not equal to 0.3, two-tail test. This piece is important. Your conclusion must be stated in full, both in statistical language, reject H0 or whatever it might be, and basically copy out the question. You must be in full context of the question. So what we have to do is write down H0 in symbols, not in words. Write down H1. Write down, are we doing a one-tail or a two-tail test? Write down the significance level. Now we have the problem. Now we need to say what the distribution is that we're using. So far we've only been using a binomial. We might be using a Poisson distribution, or we might be using a normal distribution. Then we find the critical region. The test statistic either lies inside or outside the critical region. If it's inside, you accept H0. If it's outside, you reject H0. Conclusion: there is no certainty about statistics. You cannot say that your null hypothesis is wrong or is correct. There is evidence that, and then copy the question. If you're rejecting H0, make sure your conclusion does follow what you wrote with H1. And please, you never, never, never accept or reject H1. You're not testing it. You are testing H0. You are writing down a hypothesis, H0. You are assuming that that is true, and you are either deciding that that is true or that it is not. You are testing H0. You are not testing H1. You cannot accept or reject H1.